In the late 19th century, a puzzle came in front of physics which was difficult to answer. This puzzle was of blackbody radiation curve. When an object emits radiation due to its internal temperature, the object is called blackbody and that radiation is called blackbody radiation. Wien's displacement law and Rayleigh's radiation law tried to explain this curve, but no one was able to successfully explain this curve. It seemed that it is not possible to explain it by classical physics. In such a situation, there was a need for a revolutionary idea, which could go beyond the known physics of that time and explain it. This was done by German theoretical physicist Max Planck. Not only did he successfully explain the blackbody radiation curve, but he also laid the foundation for modern physics, which is today known as quantum mechanics. In this video of quantum mechanics, we will learn about Planck radiation law. So, let's start the video. To explain this curve, Lord Rayleigh and James Jeans gave the Rayleigh's radiation law. According to this law, the energy density of the radiation is proportional to the square of the frequency and is inversely proportional to the square of the wavelength. That's why this law follows the radiation curve at the high wavelength, but due to the inverse square nature, it predicts a huge amount of radiation at the low wavelength, which does not match with the actual curve. Rayleigh's radiation law has two parts. The first part counts the number of modes of radiation present in the blackbody cavity, while the second part says about the corresponding average energy of each mode, which is equal to on an average kT for all, according to the equipartition of energy principle of classical statistics. This means that no matter what is the frequency of an oscillator, all have same average energy. Max Planck challenged this theory of classical physics and said that it is not possible. He said that if oscillators are oscillating with the different frequencies, then their energy will also be different. For this, he suggested that if an oscillator oscillating with the frequency nu, then its energy will be equal to the multiple of the frequency and a very small tiny number. This number is a constant. Few years later, this constant number named as Planck constant. If in the cavity radiations have different frequencies, then Planck calculated the average energy of all radiations with the help of Maxwell-Boltzmann distribution, which came h nu over e to the power h nu upon kT minus 1. When Planck replaced the average energy of Rayleigh's law with this, he got a new equation for energy density. This equation of average energy is bit more complicated than the Rayleigh's law. According to this, the average energy not only is proportional to the frequency of power cube, but also has an exponential term of frequency. This equation named as Planck radiation law. Now let's draw the Planck radiation law on the graph. This equation consists of two terms of the wavelength, 1 by lambda q and exponential term of the wavelength. First of all, let's draw the graph of the 1 by lambda q, then we get a curve of the decreasing nature, while the graph of the exponential term of the wavelength gives increasing curve. Both graphs are drawn at the constant temperature. When we merge both the graph, then at the low wavelength energy density follows the curve of the exponential term, because at this wavelength exponential term is dominating. But as the wavelength increases, the effect of 1 by lambda q start decreasing. At a particular wavelength, both curves are equally dominating. At this wavelength, blackbody emits maximum radiation. This wavelength is known as peak or dominating wavelength. As the wavelength increases further, the 1 by lambda q curve becomes dominating and effect of the exponential term decreases, so that overall radiation terms start decreasing. In this way, Planck radiation law successfully explained the full curve of the blackbody radiation. This revolutionary idea of Max Planck is that energy of the radiation depends on its frequency not only solved the puzzle of blackbody radiation curve, but also led the formation of modern physics, which we know today as the quantum mechanics. A few years later, Albert Einstein explained photoelectric effect using the idea of Planck, after which h nu came to be called as quanta of light. Max Planck was awarded the Nobel Prize in 1918 for this quanta of light.